All right, this page is going to go over pages 30 and 31 in your packet. So we're going to start off with number 1. It says, if a light ray strikes a flat mirror at an angle of 14 degrees, so that is your incident angle, the one that's incoming, okay, from the normal. Okay, the reflected ray will be at what angle? So this is where you got to be careful. It says it said reflected here. Okay, reflected would be your theta r, or lowercase r. Okay, so remember we talked about the law of reflection states that whatever angle you come in at, you're going to reflect at the same angle. Okay, so the answer here would just be 14 degrees, okay, because your incident angle is equal to your reflected angle. Now, if we started talking about refracted, then you would have to do the whole Snell's law thing, but just be careful with this right here. If I said refracted, then you got to use Snell's law using the whole in sine thing, okay, but if it's just saying reflected, okay, just be careful because this is a simple question to know that, I mean, it should be reflected off the same way, but it's real easy to get this mixed up because you think there's more to do when there actually isn't. Okay, so number 2, a radio wave has a frequency of 2.0 times 10 to the 6th megahertz. Okay, so 1, this is frequency. 2, be careful with this big M right here. That is mega. Okay, so don't leave this alone. So on the bottom of this, I went ahead and put it here. These are your metric systems here. So mega is right here. So that is 10 to the 6th. So if you're thinking, well, it's already in 10 to the 6th, I don't need to do anything. Okay, wrong. Remember we said whenever we added that prefix, you have to add that to whatever number you had. So instead of saying 2 times 10 to the 6th, we're going to do is we're going to add another 6 to that exponent. So your frequency is actually 2.0 times 10 to the 12th hertz. Okay, so just be careful with those prefixes. And then it says, what is the wavelength? So that means wavelength is a question mark. Now this is where everybody's like, well, you only gave me one thing. How do I do this? I'm talking about a radio wave. So remember, a radio wave is the electromagnetic waves, and remember, all of those travel at the speed of light. So that means you're doing with the whole C equals 3.0 times 10 to the 8th meters per second. Okay, so now it's basically just become C equals frequency times wavelength. So 3.0 times 10 to the 8th equals frequency, which is 2.0 times 10 to the 12th. And wavelength, we don't know. So divide both sides by 2.0 times 10 to the 12th. Just be careful. Please use parentheses. Otherwise, you can get the wrong answer. Okay, your wavelength you should get would be 1.5 times 10 to the negative 4 meters. Okay, so that's your answer there. 3, how fast is light traveling inside a piece of diamond? Okay, so 1, we're talking about light. Okay, so we're dealing with light speed. And then it talks about a piece of diamond. So I also put this at the bottom is this box right here are your refractive indexes. So this basically tells you how well light travels through different mediums. So in this case, it asks about a diamond. So my value is 2.42. So you've got different equations on this. So I've seen people try to do this. We're going to do Ni sine of angle I equals NR times sine of angle R. If you notice, did I give you any angles at all? Okay, nope. Okay, so that basically gets you nowhere. Okay, so you don't need to do that. Okay, the only other equation that has n in it is n equals c over v. Okay, so we know n, okay, we just looked at it, that was 2.42 equals c. C is the speed of light. Okay, that is 3.0 times 10 to the 8th. And then velocity is what you're looking for inside that diamond. Okay, so we're just trying to figure out how much does it slow down in that diamond. So remember, you can switch these two. Okay, so you're going to divide 3.0 times 10 to the 8th by 2.42. And you get a velocity of 1.24 times 10 to the 8th meters per second. Okay, so again, that's still very fast. So light still travels very fast in diamond, okay, but since it's so dense, okay, it does slow down. Okay, so 4, what is the critical angle for a diamond air interface? Okay, so remember we had this equation right here. Is critical angle was inverse sine of -1, okay, of NR over NI. Okay, so you got to figure out, it just says diamond air. It doesn't say which way you're going to. So diamond we know is 2.42. If you go down to this box on the other page, air is 1.0003. Okay, so now you know your indexes of refraction. Okay, so anytime a critical angle happens, it always happens from more dense to less dense. So your original is your more dense, so that means Ni would be your diamond. Okay, and your less dense is the one it's going to, so this would be your NR. Okay, so what you're going to do is you're going to plug in, so inverse sine of NR over NI, 1.0003 over 2.42. Make sure you're in degree mode, otherwise this won't work. Okay, and then you should get an angle of 24.4 degrees. So that is the critical angle that you could come in at where it would still refract, but now it'll refract at 90 degrees. So remember on the last video I talked about is, let's just say you didn't know which one was which, and let's just say you put 2.42 on top and you put 1.0030003 on bottom. Okay, the good news is your calculator won't let you do this because you're going to get an error symbol. So if you get an error symbol, that means you can't do it, so that you actually got to flip it and it won't work. I can't do it. Okay, so number 5. The speed of light in a certain glass is 1.8 times 10 to the 8th meters per second. What is the refractive index of the glass? Okay, so that means we have the speed of light in that certain material. We don't know which kind of glass it is. That means we're actually looking for what is the N. Okay, so basically how dense is it? So N equals C over V. So N equals 3.0 times 10 to the 8th over V, which is 1.8 times 10 to the 8th. Okay, so divide those, and you get a refractive value, a refractive index of 1.67. So how many light years did a photon travel if it was traveling for 895 hours? Okay, so don't get hung up on a photon. What you care about is we're talking about an object moving at light speed. Okay, and 895 hours, I can't have that. Okay, so I need to multiply that by 60 minutes, because there's 60 minutes in an hour, and then multiply that by 60, because there's 60 seconds in a minute. Okay, so what that does is that gives you a time of 3,222,000 seconds. Okay, so I'm in seconds now, so we're good. Okay, so we're going to do V equals D over T. So our velocity is the speed of light, 3.0 times 10 to the 8th. Okay, so that's V equals D over T. We're looking for basically distance. Okay, so 3.0 times 10 to the 8th is our V. Distance we don't know. And our time is 3,222,000 seconds. So multiply both sides by that, and you get a distance of 9.67 times 10 to the 14th meters. Now it says how many light years is it? Okay, that would be how, if I asked you how far did it travel in that time, then you'd be good. But remember, light years is 9.46 times 10 to the 15th. So you're going to divide that by 1 light year, so 9.46 times 10 to the 15th. Okay, because that is what 1 light year is. And so that means you get 0.102 light years. Okay, 7, what is the distance traveled by a photon in 53 light years? Okay, so I'm going to do, this one kind of printed out weird, so I'm going to do 7 right here. If I know 1 light year equals 9.46 times 10 to the 15th meters, okay, what I can do is, if I want to know how far you travel in 53 light years, just multiply that by 53. Okay, so take that number and multiply it by 53, and you get 5.014 times 10 to the 17th meters. And that's your answer there. Okay, I'm going to split this up right here. So 8 says, draw a ray diagram of a ray light passing from a less dense to a more dense. Okay, so remember we talked about, here's my surface. Okay, here's my normal line. Okay, we have our incident ray. Our incident ray is coming in. Okay, so this is your incidence. This is your incident angle, okay, your original angle. Then you have the reflected angle. So then you have theta r, and there's your reflected. So remember, those angles are always the same. Okay, so we're going from more dense to less dense. I'm sorry, from less dense to more dense, so less to more. So what's going to happen is when you do that, remember, it makes it more difficult. So what's going to do is it's going to slow it down, and it's going to pull that angle a lot closer to that normal line. Okay, so this angle right here, your refracted angle, or theta r, okay, is now going to be smaller. Okay, so that means your theta I is going to be bigger than your new refracted angle theta r. Okay, so that's what that would look like. Number 9, draw and label a diagram. So now we're going from more dense to less dense. So let's draw our barrier again. Okay, let's draw our normal line. Okay, we're going to have our incident ray. Okay, so incident ray is coming in. We have our incident angle. We have our reflected ray, our reflected angle, And now we're going from more to less. Okay, so that happens is, remember, you're going from something hard to something easy, so now it's going to actually make it harder. Okay, well, I'm sorry, it's going to make it easier, so that angle is going to take off. Okay, so that means my angle is going to get further away from the normal. Okay, so my theta r is bigger now. Okay, my refracted angle has gone away from the normal. Okay, so that means your theta r is now bigger than theta I. Okay, 10, give 4 examples of using the phenomenon of total internal reflection. So this one, I'm not going to really ask questions on this. It's just so you can actually see how this is actually used. Okay, 1, fiber optic cables, because you don't really want refraction. You want reflection because the whole goal is to get signal back. Okay, so fiber optic cables. Okay, optical fingerprint scanners. So optical fingerprint scanners. Okay, your automatic windshield wipers. Okay, so basically what happens there is you have a little infrared sensor that sends out an infrared light, okay, to your windshield, and when it picks up that moisture and stuff, it refracts the light, and it basically says that water's there, and that's what turns it on. And then endoscopes. So endoscopes are cameras that are used to usually look down certain areas in humans, so you'll find about that later in your life. Okay, 11, give 4 examples of using sound waves in medical devices. So we have like our stethoscope. So whenever they listen to your lungs, you have a stethoscope. Okay, you have ultrasounds. Okay, so one day and stuff, if you're going to look at babies before they're born and stuff, they use ultrasounds there. Hearing aids. And then kind of tag along that would be cochlear implants. Would be another one. So again, I'm not really worried about knowing these. This is just so you can see how these are actually used in day-to-day life. All right, that'll end that one.